We are going to study error diffusion dithering. We have a situation where our display surface can only display a reduced set of colors. For example, a printer typically only has 4 ink or toner cartridges: cyan, yellow, magenta, and black. An RGB color image containing 16.7 million colors will need to be reduced to just those 4 colors for printing. The example here is that we wish to display or print a grayscale image from black to white on a printer with just black ink. We could set all pixels below 128 to black and all others to white in a process known as thresholding. This would result in the bottom image that we can see there. By using dithering techniques, we introduce noise or patterns which redistribute the black pixels. The introduction of these techniques gives the impression that we have more colors available than there actually are. Both of these grayscales still only contain black or white pixels, but now we have a better impression that they are a black to white grayscale. The top image uses patterns, whereas the bottom image uses the Floyd-Steinberg algorithm to create noise. These techniques are also used for color images. For example, you can see these patterns on large-scale posters or in color prints if you use a microscope. Remember, printers often print at thousands of dots per inch, so these very fine dots are hidden from us at that scale. The photograph at the top left is changed to have a reduced color palette of 256 colors underneath. Instead of nice smoothly varying blue sky, the pixels can only take one of a few different hues of blue. Thus we see these blocky regions of colors and contours appearing in the sky. These are known as MAC bands. There are still only the same 256 colors in the top right image, but error diffusion noise has improved the appearance of the image. When looked at from a distance, the sky appears to look the same as the original. It is only when we look close up that we can see the pattern. The same is also true of the pattern dithered image below. This next slide demonstrates a simple approach to creating a black and white image from a color image. First, the image is turned to grayscale by adding the RGB components together and dividing by 3. Secondly, this gray value is compared to 128 and all values less than that are set to black and the remaining are set to white. When we introduce new algorithms, it's a good idea to test them to see how well they improve images. We'll use a very simple error metric of working out the difference between the total brightness of the two images. This is not perfect, but it introduces the topic of error to you. We'll use as practice the 4x4 image on the left with intensity values between 0 and 255. The total intensity of those 16 pixels is 2360 and the average intensity is 147.5. If we threshold the image, we obtain the image on the right, where the pixels brighter than 127 are set to 255 white, and the remaining are set to 0. The total intensity of the new image is 2550, and the average is just below 160. The total error difference between the images is 190, and the average error difference is 11.875 per pixel. We could imagine a very bad case where all pixels are 127 and are therefore set to 0 in thresholding. In this case, the average error per pixel is minus 127. It is minus 127 because we are taking the new image minus the old image, and the new image is too dim compared to the old image. Now we will study the algorithm of error diffusion dithering on the example 4x4 image. The main feature of the algorithm is that it determines whether a pixel should be black or white and then passes on the error to a neighboring pixel. On the right hand side we can see the input to the algorithm, which is the 4x4 image itself, and the error that we wish to carry to the neighboring pixels is initialized to 0. The left-hand side shows the two initialized variables for the threshold and the maximum intensity. Remember that we are working with a 0 to 255 image. Then we see the code that is executed at every pixel. The first line adds the carried over error to the currently considered pixel. The pixel is then checked to see if it is below the threshold. If it is, we display it using a black pixel and pass on the pixel value as the error. Otherwise, we set the new pixel to white and pass on the error as the pixel value minus the 255 we have just used to display white. This slide shows the application of the algorithm to the input image. First of all the black numbers in the center of the squares are the original pixel values. The arrow indicates the direction of travel of the algorithm. We start at the top left pixel and then work along to the end of the row. Then we move down to the next row and work backwards. We zigzag down the image. For the first pixel, the value is 100. This is displayed using a black pixel because it is below the threshold. We then pass the error of 100 to the next pixel. So in this box, the error is indicated by the cyan color at the top. This error of 100 is now added to the original pixel value to give us the new value of 200. 200 is above the threshold, and so this pixel is displayed using 255 white. The error is now determined by the second if statement, and it is 200 minus the 255, which gives us an error of minus 55. We add the error of minus 55 to the 120 to give us 65. This is less than the threshold, and so it's displayed using a black pixel. And then the error of 65 is passed along to the next pixel and added on to give you 205. The error will be 205 minus the white pixel of 255, which gives you minus 50. This gets added to the next pixel along. We've gone down a row. And this gives you a new pixel of 100. This is displayed using a black pixel, and the error of 100 is passed on to the next pixel. So we continue along the line in this way and then move down and continue backwards along here. So in this case, when we sum the error and the old pixel value together, we got 210. 210 minus the white pixel that we set this pixel to gives you an error of minus 45. Add that to this pixel, you get 125, and this gives you an error of 125 passed on. We now add this error to the 200, and this gives us a pixel of 325. This is outside the range of 0 to 255, and so it indicates that we should be using type integer rather than type byte to store these values. 325 is above the threshold, and therefore this pixel is displayed using white. And then the error is calculated as the 325 minus the 255, which gives you a plus 70 in this case. We add that to the neighboring pixel original value and we get 320. This is above the threshold, so it's displayed using white, and then 320 minus the 255 gives us the plus 65 here, which gets added onto this pixel to give 265. This is displayed using white, and the error will be plus 10, which gets added onto this pixel to give us 180. This is above the threshold, so it's displayed using white, and 180 minus 255 is minus 75, which gets added onto the original pixel value there, giving us 65, which is displayed using black. At this point, the error would be 65. This would be passed to the next pixel, but since we're at the end of the image, this doesn't get passed anywhere, but we could use it to check the error of the image later on. We will now calculate the error of the new image. The input image is the one that we can see on the left-hand side, and we just carried out error diffusion dithering on that image to produce the black and white image that we can see on the right-hand side. We will follow the same process as before, so we will work out the total intensity of the input image, and that is 2360, and we'll work out the total intensity of the new image, which comes out at 2295. The average pixel value in the input image is the 2360 divided by the 16 pixels, which is 147.5, and the average intensity in the new image is just over 143. If we now calculate the difference between those figures that we have, we can see that the total error between the two images is 65, or minus 65 in this case, which shows that the new image is 65 gray levels too dim. And on average, it is 4 gray levels too dim between the two images. If you now look back to what we had for the original error calculation, where we just did a threshold, a simple thresholding, you can see that this new approach produces a slightly better error on this image. We will also consider the image that we had before, where every pixel was 127. In the case of thresholding, for this image, every pixel would be set to black. But we can see the error diffusion dithering passes the error across to the next pixel, and therefore some of the pixels will be set to white, as we have in this case. The error here is now the 254 minus 255, which is minus 1. Add that to the original value to get 126, and that's the error that gets passed on to the next pixel. So we can see that we end up with an image which will have white and black pixels alternating, which will give us the impression that this is a grey image. If we now do an error analysis of this particular case, the input is on the left-hand side, and we previously calculated the total and average intensity. And on the right-hand side, we see the error diffused image, the black and white image that we get as a result of applying error diffusion dithering to that input image. In this case, the new total intensity is 2040, the average intensity is just over 127. The error difference between these two images is very low, so it's just a total of 8 or an average of 0.5. So we can see that in this particular case, error diffusion dithering has improved the situation considerably. We will end up with an image which does look quite grey when we look at it from a distance. We'll now look at the image that we had at the start. So this is the vegetable bowl that we saw earlier on. Previously, we converted this to a grayscale image and then thresholded it so that we had a black and white image. We couldn't really discern much in that image, but now if we apply the error diffusion dithering to that image, we can still see quite well that this is a bowl full of peppers. And the image on the right has only two colored pixels in it, black and white, but we do perceive levels and different levels of gray because of the error diffusion dithering and the noise that has been introduced to avoid the MAC bands that we would otherwise see. So far, the process we have seen has passed the entire error onto the next undrawn pixel, where that pixel could be on the same row or on a different row if we're at the edges of the image. There is a variation to the algorithm known as the Floyd-Steinberg error diffusion algorithm, and this passes on the error to the undrawn neighboring pixels. So if we consider the light blue pixel that we have here, all the red pixels have already been determined as being black or white, and we're now looking at the current blue pixel. Once we've calculated whether that should be a black or white pixel, we can calculate the error as we did previously, but then instead of passing it all onwards to the right-hand side pixel, we're going to pass a proportion of the error onto each of the 4 undrawn pixels. So in this case, we're going to pass on the error to alpha, beta, gamma, and delta, and the errors are going to be calculated according to the values that you can see in the array there. This slide shows the error being passed on to the undrawn pixels. So the first bit of code is the same as before. It determines whether a pixel is black or white according to its value in the threshold, and then determines the error that will be passed onwards from that pixel. Once we know the error, we can weight it according to the alpha, beta, gamma, delta, and then pass it on to the appropriate neighbor. So inside those array indexes, we are working out the neighbor that we need to pass that particular error onto. When we get to the last row, Floyd-Steinberg would simply pass all the error onto the next pixel since there is no row below. When we get to the last column, it will pass the error to the next 2 undrawn pixels rather than the next 4 undrawn pixels. Also, we traverse the pixels with a zigzag stride as before, so the pattern by which the error is passed on will be flipped on each row.